We will continue with the discussion on this protein folding pathways, energy landscapes, right. So, we will what I will do again is we will do a brief recap of what we did yesterday from the section of the protein folding pathways, and then go on and see the other funnels and all those things. So, what we were saying yesterday was that if you would be defining the protein folding problem, it would be three separate problems. One is the folding code, essentially the forces involved in defining the native state from the unfolded state. Then if you are given a specific sequence, whether you would be able to predict the structure based on some logic, and then it is the speed. And what we said was this is something which is very well known in the protein folding field, Levinthal's paradox, where what you consider is that if you are in the unfolded state, then you have so many configurations to search for, to go through, that it takes you time to go to the final native state. But proteins seem to do it in a pretty quick time, decent time. And then how do you resolve this issue? How do you resolve the fact that on one hand the protein has to go through so many conformations, right, and then on the other hand it still is being able to fold within a reasonable amount of time. So, that is essentially what the paradox is. Okay. So, that is what it says. This one talks about the nature of folding pathways. So, Anfinsen had proposed that there is nothing to do with pathways, everything is thermodynamics. Okay. Thermodynamics is the one which controls it. And then Levinthal said that if it's protein folding is like or finding the native state is like finding a needle in a haystack problem, and which would preclude or which would inhibit the protein from actually doing a random search. That means the protein, if it starts doing a random search, then it just takes too much time for the protein to go through the whole conformational space. So, it decides, okay, I will not do it. Instead, there must be some specific directions, some specific pathways, some something specific which makes the protein fold down within to the native state within a reasonable amount of time. So, that means there must be having some specific folding pathways, right. And this was the quotation from the Science magazine, which had was an analogy which said that the computer would be taking about 30 years, but still a protein can do it within microseconds. So, then the thing is, does it really go to that conformational search? Okay. So, this was about protein folding being considered of two goals. One was the thermodynamic control independent of pathways, then the other was the kinetic control, not really focusing on thermodynamics, where in this case you can give rise to local optima. Okay. This is a kinetic control. So, this was the long standing riddle, again the same thing. If the structure of the protein is determined by its thermodynamic stability, and if the kinetics of the conformation search are so slow, then how is it possible for the protein to reach pretty rapidly to that native thermodynamically stable state. Okay. And then there was this calculation which showed you that if you would take 100 residue protein, take the minimum of the times available, that means one is the minimum conformation, which is like just 3, the other one is if you look at the time, what was the time? It was 10 to the power 13 structures per second. Now, I did not tell you too much about the time issue here, which is being involved. Now, 10 to the power 13 structures per second, that means it's maneuvering through one structure in what, 10 to the minus 13 seconds, right. Now, think about this. You have heard of femtoseconds, right, 10 to the minus 15 seconds, right. There are lasers which with which people use lasers to look at dynamics in molecules, maybe a protein or many simple molecules, and 10 to the minus 15 is a very short time. So is 10 to the minus 13. Now, try to understand the relevance of 10 to the minus 13. 10 to the minus 15, the relevance will now be not that much clear, because we do not have much of idea of lasers. But let us talk about 10 to the minus 13. Now, think about this. If you would be trying to break a bond, right, if you would be trying to break any bond between two atoms, right, what do you think is the fastest time in which you would be able to break a bond? What do you think? There should be something there should be something which will tell you that maybe this is the fastest I can break a bond. See, I am not talking about energy, I have given enough bond dissociation energy, that is taken care of. What do you think a bond would need to do before it breaks? I almost gave you the answer. Let us go back one more step. In quantum mechanics, you did something known as particle in a box, right? What was the next system you studied after particle in a box? Harmonic oscillator. What was the essence of the harmonic oscillator? How do you apply it to a bond? It is your bond potential, isn't it? Half kx squared, right? So that means you are asking your bond to behave as a spring, right? And then obviously in harmonic potential you took into account anharmonicity and all these things. But then if the harmonic potential or this stretching frequency, this is talking about vibration, then tell me what should a bond do before it breaks? Well, it has to vibrate, right? It will be vibrating. So then what is the fastest time scale? The fastest time scale is the time it will take to vibrate, at least one period, right? So typically the vibration time period is 10 to the minus 13, 10 to the minus 12 seconds depending upon what bond you have. So now do you understand the significance of this 10 to the minus 13 structures per second, 10 to the minus 13 seconds for one structure? So you are almost equivalent to what? A bond vibration, and you cannot go faster, right? Because you already know that the fastest time scale you can break a bond is 10 to the minus 13, right? It is not 10 to the minus 14, well, it is not 10 to the minus 15 definitely, right? So this is the minimum time a bond would take to break, and hence that is what we have used here. So think about this. So then there is the relevance of this time scale. We could not have gone any faster, as simple as that. And obviously we can go slow, but what people were trying to do was you take a minimum of a conformation, say 3, and then you take the minimum time possible, which is 10 to the minus 13. That is the fastest time possible, 10 to the minus 13. Okay. But still, when you did the calculation, what it gave you was a time which was way beyond what we could fathom, right? Then obviously there is something wrong, and this again precisely is the Leventhal's paradox. So then we talked about the energy landscape. We described what an energy landscape is. I will not go through it again, and we said that it's a proper energy landscape is more like a funnel. So that means on top a funnel is always broad. So that means on top you have the unfolded state. You are looking at the essentially the entropy of the unfolded state, and the entropy being so huge for an unfolded state, that is why the top portion, which is the unfolded state, is so broad, right? And then as you go down to the native state, what you do is the protein starts losing entropy, and hence the funnel slowly narrows. Okay, but also look at one thing. I am showing a funnel and I am using both of my hands. Now there is a significance to this, and we will come to that soon. So then we started going into this different funnel landscapes, and the first one we encountered was well, this was what your vertical axis and horizontal axis refer to. So vertical axis essentially is your internal free energy, and the horizontal axis essentially is your conformational freedom, talking about these bond angles. So it can be referred to as your entropy essentially. It's a conformational freedom, horizontal axis. Okay. So this is the one we started with. So again we will start from here. So what we said is that, you see, I mean this is not exactly a funnel, right? This is not exactly a funnel, it is a golf course. A funnel essentially, what does it have? A funnel does not, I mean funnel has a gradually tapering thing, right, but this is not what it is. That means you have just a flat course with the hole in the middle, and then you come straight to the native state. And the point was that whether this is a logical picture of a protein trying to fold from the unfolded state to the folded state, that was the question that was asked. Okay. And what we were saying is that the native state is here, this is the whole flat landscape, right. So that is what it said the hypothetical flat playing field. Now as I have shown here, a denatured state would be having several different conformations, right. So one of the conformations can be here, another conformation can be here, one conformation can be here, one conformation can be here, right. Being so, see each of these conformations does not know where to go. What does it mean? That means it is a flat playing field. So, each and every direction is equally possible, is equally probable, because see there is no bias. No one tells this particular conformation or this particular unfolded state where to go, because it sees a flat playing field, and if we consider a ball rolling on a flat playing field, it will just go on rolling, right, without talking about frictions and all these things. The same thing happens here. It can go in any direction depending upon where it wants to. At every direction its probability is the same, it is an equal probability situation. So, what do you mean by going in different directions? By going in different directions we mean is this: every point on this energy landscape signifies what? A specific conformation. Remember, that means if it is trying to go in different directions, it is trying to sample what? Different conformational spaces, okay. And because it is a flat playing field, what does it mean? That means each and every conformation of the flat playing field has the same energy, because your y axis is what? Energy. So, there is no energetic bias for you, right, because you do not distinguish them in terms of energy, they are equi-energetic. That means each and every one would be trying to be sampled. So, this is your random search space, and so same will happen for this one, same for this one. Now, look at something which is I have drawn here. Let me draw somewhere here another. If you look at this one now, say this is I say 1. So, what will happen is it can go this way, it can go this way, it can go this way, but the moment it comes this way, what happens? The moment it comes this way, then it immediately finds itself falling in the hole. So, now it cannot go out of the hole, because that reverse is very steep. So, the moment it comes in, it goes straight in. Okay. So, that means only a very small fraction of the total space having these unfolded conformations would actually be able to go to the native state in a decent amount of time. For the others, you never know. This is based on this picture. So, that was the problem behind taking a golf course landscape or a flat landscape. Okay. Is it clear to everybody? So, again as I said, so Levin's major objection was that given the vast number of configurations that a protein will have to sample on the flat potential, remember it is a flat potential, the protein will be having a serious search problem. It is really serious, and by random searching it would not be able to find the native state n. Well, it would be able to find the native state n given that amount of time, right. So, within the biological time frame it would not be able to do it. Okay. So, then obviously and people try to improve it. So, what they did was they went for a path based solution. So, what you do is in the flat landscape everything was just flat except the hole in the middle. Now, what you do is you say okay, on the flat landscape at one point I will dig a tunnel. So, tunnel essentially is what? Your pathway. Okay. So, what it means is you think about a conformation here, you think about a conformation here, you think about a conformation here. These are experiencing the same flat landscape as you had in the previous slide. Okay. So, that means these conformations experience the flatness of the landscape. Okay. Now, what about a conformation which is here, which is represented by A? If because this is also a part of your landscape, you will be having a set of conformations defined by A which would be there. And if the conformation starts from A, then what will happen? It will not have to search because the tunnel is already made for it. What does it mean? It means that its path is already chosen for it. That means it has a specific pathway. Remember, we are talking about folding pathways. So, what will immediately do is it will just follow this like this and then come in straight. Okay. Now, possibly this is also not very logical picture, but think about the improvement from the one which we discussed previously. The previous one had no bias, there was no path chosen for it, but at least this one what you do is you introduce what? The concept of a specific pathway, a specific direction. That is what it is. So, that means here you can see that it says this is very important. So, that means the conformational searching is more directed, that means you are giving that set of conformations defined by A, that A a direction. Okay. So, up till that point we are okay, but then what is the problem you think? The problem is, as we discussed briefly yesterday, in the denatured state you do not have only one conformation defined by A, you will be having all these other conformations, right. So, that means you will be having a conformation which is defined by, say this is B, this is C, this is D, I can have something which is E and so on. But then what will happen to the other ones? They would be facing the same problem as before. So, then in one sense we introduce this concept of a pathway, but in the other sense we actually do not end up solving the problem, because you are still taking a lot of time. As you have said, the tunnel is only at one specific place where only one set of conformations can come through. Okay. So, then if you go to the next slide, that pretty much tells you what the advantages of this one are. So, starting from a denatured configuration A, the pathway model suggests that the folding protein molecule progresses through a tunnel or gutter to the native structure N. Okay. That is good. Now, the process is more directed than a random search. Obviously, you have a path which is chosen for you, so that is why it is more directed. Okay. And then the pathway therefore refers to a well defined sequence of events. That means once you are in the path, then you know where to go. That means your sequence of events is pretty much defined for you. Okay. Now, what are the thoughts against this? The thoughts are, our pathway can lead, so it will be lead from point A to N. However, protein folding does not involve starting from a specific conformation A, it will be having a host of conformations, right. Again, the denatured state is not a single point on the energy landscape. All the points on the landscape except the point referring to the native state N is a denatured conformation. That means, if you are talking about A, well and good, A satisfies, but what about all the other configurations B, C, D, E and so on? You are not being able to solve that thing, right. Okay. So, then the final conclusion is the pathway model is too limited in its applicability. The golf course model was absolutely not making any sense. The pathway model at least makes sense in terms of the pathways, but still it is very limited, right. So, can we improve on this? So, then the idea was, see, we will not be talking about tunnels, what we are going to talk about is funnels. Now, the golf course essentially was not a funnel. Yes, it was broad on the top, but then it soon became very sharp. So, it is in that sense it is not a funnel. Then in that golf course introduced what? A pathway which is a tunnel. So, it became a tunnel landscape. But now what you are saying is that we should not be considering a flat landscape, we should not even be considering a tunnel landscape, instead we should be considering a funnel landscape. And you can see what there is another word out here, and this is important, it is called the new view. Essentially it is the new view of protein folding. Okay. And I will tell you why it is known as a new view. If there is a new view, then there must be an old view, right. That is why it is called the new view. So, we will discuss that. Okay. Now, look at this pathway. So, this is your funnel landscape, this is an idealized smooth funnel landscape. Now, what does it do for you? What do you think is the major difference now between this one and the one you just saw in the previous slide, that is your tunnel landscape? Very good. That means it does not matter which denaturation conformation you start with. So, for example, see it is already here, right. You can look at these black points, there are these black points out here, right. So, it does not matter, you can see there are black arrows leading to the native state. That means, if this is your conformation A, this is your conformation B, this is your conformation C, all of these because of the slope of the landscape would be going to the native state, you know, following definite paths. We do not want to know what path it is right now. So, not only A, B and C, if I put another one say out here which is D, another point out here which is E, another point out here which is H, all of these would manage to go down, right. So, they would still search, but now you think about this, this search is not just a random search. What kind of a search is this? This search is referred to as, let me tell you, is referred to as a guided search. And what is guiding? What is guiding is, well, there will be many things can be guiding, but at least in this case you know that if E is here, if E is here, if it comes here, then it immediately has an energetic stabilization. So, that is a guiding potential for it, then it goes on moving down. Okay. So, now what you have done is the golf course, no slope, flat, the tunnel you had a pathway, but now you bring about a funnel. That means what it tells you is, no matter where you start from on the energy landscape, each and every conformation has the probability of going down to the native state without doing too much of a random search. It will still do a random search, but see, once it goes to this side where you have a sloping, you have a slope towards the native state, it will start going towards the native state. Each and every conformation, does not matter where you are on the energy landscape. Okay. Now, there is one important thing connected with this. So, what does it mean? What it means is, possibly this funnel model is talking about parallel pathways. Now, this is very important. What do we mean by parallel pathways? Parallel means that all these things are happening simultaneously. See, for example, A, starting from conformation A, you can go down, starting from conformation E, you can go down, starting from conformation B, you can go down, right. But it is not that B will be dependent on A, or A will be dependent on E, or E will be dependent on C. Each of these can by themselves go down to the native state, maybe at the same time, right. That means what you are doing is you are approaching. So, this is your entropy landscape, this is your essentially entropy, right. You have all these delineated conformations, and what they are doing is they are moving down parallelly at the same time along the landscape towards the native state. Do not you think it is going to save you a lot of time? Why? Because now all the conformations are moving down together. So, together, I do not mean together means exactly the same time, but just they are moving simultaneously towards the native state, instead of say A going to E, going to B, going to C, going to H, and then moving down to the native state. Is it clear or not? So, that means you are talking about parallel folding routes. You are talking about, it is not just one sequence of events, it is what? Multiple sequence of events, multiple pathways, multiple folding routes. That is what this parallelism, that is what this parallel word signifies. Okay. That is why funnel landscape is so important. For the first time, that is why it is called the new view. For the first time, it gave this idea of a parallel folding pathway situation. That means it does not matter where you start from, each and every conformation has the potential of going down the native state just by itself. Okay. Okay. Now, remember, this is called the idealized smooth funnel landscape. Now, what does this word smooth mean? The word smooth means that when you are coming down the landscape, you are not encountering any, right, you are not encountering any local barriers. That means it is just a smooth sailing, right. It is like just moving down a slope which is a free slope without any obstacles. But remember, what we said was our energy landscape can be having hills, can be having barriers, right, can be having all sorts of things, right. So, then probably, though this does solve this random search problem through a multiple parallel folding route, but then it is not an ideal situation like your ideal gas law. Ideal gas law it gives you all the basic informations about a gas, but then it is not the one we talk about. Why? Because we know in real system we do not have ideal gases. There will always be attractive interactions or interactions intermolecular forces between these. The same thing is happening here. There is an ideal funnel, but then how should a real funnel look like? So, this funnel then is a solution to your Levinthel's paradox. What does it say? Each different unfolded conformation starting from different points on the landscape can reconfigure towards the native state n. Okay, that is what we just said. Each of the above configurations can follow a different sequence of say dihedral angles. Remember, dihedral angles were referred to as this conformational conformational coordinate which corresponds to the entropy. Okay. they can follow independent of each other. So, this essentially eliminated the pathway terminology. I do not need a pathway. It resolves the paradox about pathway dependent and pathway independent processes. How? It says that funnels imply parallel processes and ensembles. Pathways imply what? If you are on a path, that means you only have to follow that sequence of events. You do not necessarily have to follow that. You can still do that, but fold parallelly at the same time. Now, obviously, you have to understand this. If someone would be thinking about a protein folding logically without thinking about this new view, which is this funnel model, what would you think? You would just think this. You would start from, say, an unfolded state and maybe go through a sequence of intermediates, say I1, I2, I3, I4, and finally reach the native state. That is your pathway model. That means you are defining the pathway. It has to go through that intermediate I1, it has to go through intermediate I2, and so on. That is a sequence of events. That is your pathway. You have defined the pathway for the protein, and that is called the classical view. I will come to that. But this new view totally said that okay, maybe we should come out of that comfort zone and think about it differently. So, then what is the funnel idea? So, folding chain progresses towards lower intra-chain free energy by increasing hydrophobic core formation, stabilizing hydrogen bonding and other forces, and in the process the chain's conformational options become narrowed, right, because once you start folding, then your conformational option is getting narrowed ultimately towards the native structure. Again, this is your funnel. Okay. Now, this is possibly an idealized landscape. How is it different from the one you just saw? Here you can see what happens is you have these, what are these? You see, these are these hills, right? Say this is a hill 1, a hill 2, and so on. You can have many hills. This is just a kind of a schematic. See, now what will happen is, suppose I have a conformation which is starting from here. If it comes down, it hits the hill. So, that means it has to either bypass it like this or go over the barrier. That is one way of looking at it. Then if you look at this one now, if I start if there is a conformation starts from here, what can it do? It can come straight like this and go down without actually encountering a hill. Okay. So, obviously, we talked about parallel pathways. We said that there is no well defined pathway, whatever pathway it wants to take, it can take, does not matter, as long as it is energetically feasible and it falls within the required amount of time. But it also tells you one thing. What does it tell you? It tells you that this protein folding is really heterogeneous, do not you think? That means if you are starting from here, say this is point A, this is point B, that point A would come, reach a barrier, then it will think what I will have to do. Either if it has the energy, it will go over, or it will try to sidetrack. That means that guy, that conformation is taking more time. The other one, which is B, it does not have to think like that, because it is not encountering any barrier, it is going straight down. So, that means just in one ensemble of denatured molecules, you can be having many pathways depending upon how these things go down the folding. So, that is why protein folding is said to be very heterogeneous. So, now you understand why if a process is very heterogeneous, why it becomes also so complicated. It is very hard to pin down on one specific process, because whenever you look at a signal, whenever you look at an observable, what do you look at? You look at, it is like an ensemble average, right? You look at signals of all these molecules together giving you an average signal, but you exactly do not know which path this protein conformation A took, which path protein B took, and so on. So, again the concept is here gives rise to this concept known as heterogeneity. There is another important concept that comes out of this funnel landscape. Okay. See, that is why it says it is a rugged energy landscape with kinetic traps, energy barriers, so hills, and narrow through-way paths, the one which is followed by B to the native state. It is just not one path, it has multiple paths. So, this is a schematic now. Finally, this one would give you a lot of information. So, see, there is a beautiful schematic. it tells you pretty much whatever we have discussed right now. It is, you are looking at a funnel now. So, in the shaded portion what do you have? Say this, you look at this one, you look at this one, what are these? These are different conformations of the same state, which is the unfolded state, right, and they are occupying different points on the free energy surface, right. Now, you see all of them are starting to fold from their respective point without trying to go or interconvert between themselves. Well, they can, but then from here they can also see all of the black arrows are leading down from their respective points towards the native state. Okay. So, this is just what it is talking about 1, 2, 3, 4, 5, 6 representative unfolded states, but then you can understand that you can be having what, many unfolded states in between. Second, see it is not a smooth one, right. So, this one can come in and get trapped here, get trapped here, get trapped here, get trapped here. These are what, remember we talked about this kinetic folding, I mean they would be having local minima. So, this intermediates would be some certain intermediates which would accumulate during a folding pathway. So, these are just somewhere, it is not your global minimum which is your native state, it is just that when you are moving down you suddenly find there is a hole, but that hole is not the hole which corresponds to your native state energetically. Now, this one, remember everything finally is governed by thermodynamics, right. So, this one will soon realize and it will go out and come down to the native state, but in its own sweet time. Okay. So, now this is misfolded protein is typically a kinetic intermediate. It is typically a kinetic intermediate. It is not thermodynamically stable, but kinetically it is feasible, that is why it is called a kinetic intermediate, right. And then finally, you have the native protein, you never know what can come. So, this is the heterogeneity in protein folding we are talking about, but anyway. So, but I think this representation given in this paper is an excellent representation of what can happen or what an unfolded protein can go through if it has to finally go to the native state. Now, remember this is just a schematic representation, it does not have to exactly follow that path. Okay. So, then I told you if we are talking about the new view, whatever we talked about was the new view, what is the classical view then? The classical view is this. It depends upon a sequential model of protein folding. That means, you start from a denatured state D and then it says that you have to go through I1, I2 and so on until you reach N. This the pathway is chosen for it, you are defining the pathways for it. See, that is a logical view too, right. I mean you know that it starts from the denatured state, maybe it has to go through these intermediates which will finally help it to go to the native state, that is fine, no problem. So, these are two different views, one is your classical view which is a very logical view too, and the other one is your funnel landscape view which is your parallel folding pathway view. It does not exactly follow a sequence like this what you have said in a classical view. So, as you can understand, if you are going to have two views, then you are going to have experiments or research which would be trying to prove one, or the set of experiments which would try to prove the other. So, evidences are there for both essentially. Okay. Right. Now, let us look schematically at a few types of protein folding. I mean what are we talking about. So, suppose we look at this A, we are starting from denatured state. A denatured state, it says that cooperatively, that means at the same time you form all the native interactions and finally get the native state on your right. So, this now is what, tell me, this is, isn't this a 2 state? That means you only have a denatured state and then you finally have the native state, nothing in between, because you remember when we talked about this 2 state model in thermodynamics, right. That means anything in between is not populated, you just only have these 2 states. Now, you can have part B, you can have another thing in which it starts, you have an intermediate like a molten globule you saw in the previous thing, and then this again rearranges to form a final native state. Now, remember I am not telling you what the molten globule is, but what does molten mean? Molten means melting, right. If this is your final globule, if this is your final native state, see how this one is different from this. This portion and some portions of these do not have the structure. That means, you see these beta strands out here, these blue ones, these are not yet developed here, but a lot of the alpha helical packing or a lot of the alpha helices are already developed. So, what does this mean? You are not talking about a fully denatured state. So, you are talking about a part of a native state which has melted, that means which has denatured, that is why it is called a molten globule. So, a molten globule is not necessarily the denatured state, it can be very close to your native state, retaining a lot of the native state structure. Okay. So, like I will give you an example. I have told you about this protein before, apomyoglobin. Apomyoglobin at a certain pH is equal to 4, has a very well defined molten globule state, and that is why it is one of the most important examples of the existence of a molten globule state. Apomyoglobin is very well defined. And the other one is, now what you are looking at is, you are looking at different domains, say of a multi domain protein, that means you have one domain, one domain, one domain. So, one domain folds first, a second domain folds, and then finally they come together and give rise to the final 3 dimensional structure. So, this essentially happens for proteins which have not one domain, it is like hemoglobin. You think about hemoglobin, how many units does it have? 4. So, what you can think about is, each of these 4 units first fold by themselves, those are the respective domains, say, then once they are folded, they come close to form the final structure. So, that is essentially what is talking about formation of the remaining structure, right. Okay. Let us start with the mechanism. So, we have talked about some of the models. Model means the pathways, that means the funnel landscape and all these things. Now, can we talk about some mechanisms, how exactly this folding has happened, what sort of mechanism can we talk about? So, let us look at 3 pretty well defined mechanisms. Look at the first one. The top one talks about a framework model. So, this one talks about a framework model. Okay. Now, what does the framework model mean? The framework model means is, so you are starting from this denatured state, this unfolded state u, you are starting from essentially denatured state. Then you can see what happens. What is the difference between this one and this framework model, this say this intermediate or this intermediate structure? What is the difference? You can see at certain points you have a blue strand, a green strand beta, and then you have a green alpha helix and a red alpha helix. So, what have you done? What you have done in this case is, it is a framework model in what sense? That means you are creating a frame. Frame means, see, if you have a frame and if you put those things together, you get the final structure, right. This is what it is doing. It is saying that when I sign for the unfolded state, I go to a state where I have a little bit of my micro secondary structural elements already solved or already folded. Why you say micro? Because there may be a very small stretch of beta strand or a small stretch of alpha helix. Now, once you have done that, then what happens is, these have to interact to finally give you the final native state. So, that means they diffuse and collide with each other. So, that is why it says diffusion and collision. So, diffuse and collide with each other. So, diffusion and collision with each other to give you the final native state n. So, that is your framework model. Okay. So, let me now actually give you the definition of this. So, the framework model says the local interactions dominate and guide the formation of secondary structural elements, that is a sequential formation of native like microdomains. This is followed by a random diffusion collision model or diffusion collision of these local elements of the secondary structure until stable native tertiary contacts are made to give the final structure. That makes sense. Okay. So, you can understand one more important thing is, if I am following a mechanism which follows this diffusion collision model, then because these different structural, these different domains will have to diffuse to come to close proximity and then interact, then diffusion would be playing a major role. And by diffusion, what sort of diffusion do you know? For example, have you heard of Brownian diffusion, Brownian motion? Okay. Have you heard of let us see, have you heard of Fick's law of diffusion, right? So, what we will do is, based on this in the next class, we will look at the diffusion process in a little mathematical detail and see what do we exactly mean by this diffusion, and see people would, based on that model, actually model this, or based on this diffusion model try to explain this diffusion collision experiment or method. Okay. So, that is what we will do. Now, the other two mechanisms, one is nucleation. So, what it says is that here what you do is you form a certain nucleus of certain elements of the structure, and then so this is your nucleus. You can see you have already formed the nucleus out here. So, this is your nucleus. So, this is your nucleus, and once you have formed the nucleus, then here possibly there is no diffusion collision. Once you have formed the nucleus, everything else now sits on it, rearranges to give you the final native state. Okay. And the third one is hydrophobic collapse. Now, before I go there, let me give you the inside of this nucleation model. So, this postulates that the formation of a local nucleus by a key residues or a few key residues of the polypeptide chain that will allow the rest of the structure to rapidly propagate around the nucleus. Okay. There is also something known as nucleation condensation. So, it is a little bit different. What it says is it postulates a more diffuse nucleus having poor stability, with stabilization requiring interactions between non-local residues. Now, what does it mean? What it means is the difference from the nucleation model is this. Remember those two small alpha helices you saw in that first slide. So, that they are supposedly stable by themselves. Now, what can happen is instead of following a full blown alpha helix, you can be following a small helical segment. Now, that small helical segment might not be very stable by itself, because it does not form the full blown interactions. So, instead what will be happening is, because its stability is poor, it will look for support from other places. So, those are your interactions between non-local residues. So, I forgot the C out here, this is non-local residues that will stabilize it, and finally, the whole thing will fall in the nucleus and you will get the native state, right. And if you go to the one of the most important models, which is the hydrophobic collapse model, what does this one say? It says that folding of a protein begins with the clustering of say few amino acid residues in the initial stages. So, if you have some amino acid residues or side chains which are hydrophobic, at a certain point of time they will cluster together. If they cluster, what will happen is they will form a small unit. The moment they form a small unit, what does it do? It says that this restricted conformation space then facilitates the formation of secondary structure and tertiary interactions. The clustering of hydrophobic residues is expected to be non-specific and hence to happen quickly. Now, what do you mean by non-specific? I mean by non-specific means it does not care about which one is coming in. What it really cares is that if my partner is also hydrophobic residue, I form that hydrophobic cluster. See, what happens when you form a hydrophobic cluster? What you are doing is, when you are forming a hydrophobic cluster, what are you doing? The moment you form a cluster, aren't you narrowing down your funnel? So, that means what are you doing? You are improving your search model, and the moment you have your search model improved, so then the protein will be taking lesser time, and hence around this hydrophobic core, first there is a hydrophobic collapse and then the protein folds to give you the native state. So, going back to the initial model, so this is what I mean. The hydrophobic collapse, you see, these are the green residues which are the hydrophobic residues, they collapse to form a hydrophobic core and then the protein folds. Now, whatever these models are trying to do, one thing is common, either is it by, if it is by this framework, or whether by nucleation or by forming hydrophobic cluster, what is it trying to do? It is trying to what? Reduce what? The conformational subspace. See, that is something which is common amongst all the models, okay, and finally it goes down to the native state. Okay, I will just show you one more thing before we get done with the class. So, this is what we are going to talk about in details in the next class, and I will show you, I will not give you these points right now, but instead I will show you one example of a diffusion collision model. You think about this. Do you remember the structure of myoglobin, which we showed sometimes during the class? How many helices does myoglobin have? No, it is A to H. So, how many helices? 8 helices. Now, if it has 8 helices, you think about this, each and every helix can be is a micro domain, say, right. I can have helix A, I can have helix P, I can have helix C, I can have helix D, and so on up till helix H. Now, think about the framework model. What did the framework model say? That initially I form micro domains, which are these, say, helical intermediates, and then they finally diffuse and collide to give you the final structure. So, what do you see here? So, this is not myoglobin, but you see you have A to G, right. So, how many do you have out here? Anyway, not how many, what I mean is, see, this is one microdomain, this is another microdomain, this is another microdomain, this is another microdomain, and so on. All these are microdomains. So, what has happened first is that these small helical traces by themselves have formed the helices first. Now, this is a framework. Now, what happens is these will have to interact. So, then you can see F and G, say, possibly come closer by diffusion. In the next one, D, C come closer by diffusion, and finally, you go down, you get your native state. So, that means once you have formed your microdomains, then they individually diffuse and collide, and they go on diffusing and colliding, diffusing and colliding. You know, some diffusions might not lead to the correct structure, then that has to open up, then other diffusions will be taking place, and finally, we will get your native state. So, this is typically what the diffusion collision model is, and myoglobin has been treated very nicely using this diffusion collision model. This is what we will look at in the next class, and for that what we will do is we will actually also look into the diffusion mathematics a little bit and try to understand what really diffusion is, and try to derive something. If you remember, there is Einstein's diffusion coefficient and all these things. So, we will try to look at that. Okay.